back. So what you guys are looking at today is 4.2, which is bike lovers. So let's go ahead and jump right in. So what we're looking at here for this first part is absolute value equations. So we want to solve for, well, it says x, but we want to solve for the variable because we don't always have x as the variable. So you can kind of ignore that direction because it's a little bit off there. So we're going to do a few of these just so you guys can really get these. When solving absolute value equations, like it says, you will have two answers. In every single one of these cases, you are going to have two answers because we're dealing with absolute value. So if we look at this first one, we have the absolute value of x equals 7. There's nothing on the outside of this absolute value symbol. So that means we're at the point where we can take and split this into two possible problems, or into two problems. So we take what's inside the absolute value symbol, which is the x in this case, and set it equal to positive 7. And we set it equal to negative 7. Because the thing with absolute value is it takes a negative number and it turns it positive, because absolute value is the distance a number is from 0. So if we have a negative number, the distance it is from 0 is a positive value, because distance can never be negative. It doesn't matter if you're walking backwards, if you're going in a backwards direction, it's still a positive movement. So that's why with absolute value, you always end up with a positive solution. So that's another thing. When you get the absolute value all by itself, like it is here in number 1, if it equals a negative number, that means there is no solution because you can't have a negative distance. So for number 1, these are our two answers because we didn't have anything else inside the absolute value to have to worry about solving with. Now on number 2, once again, there's nothing on the outside of the absolute value, so we don't have to worry about solving anything yet. So we split it. So we're going to have the equation x minus 6 equals 3 and x minus 6 equals negative 3. Now we're going to add 6 to both sides. So we have x equals 3 plus 6 is 9. So there's one of our solutions, x equals 9. Our other solution, we're also adding 6 because we don't change the sign inside the absolute value. That cancels. So we have x equals negative 3 plus 6 is positive 3. So our other solution is x equals 3. So those are our two solutions for this. If we plug these in, 9 minus 6 is 3. The absolute value of 3 is 3. 3 minus 6 is negative 3. The absolute value of negative 3 is positive 3. Okay. Is number 4. So now on this one, notice it equals a negative number, but we have a negative 9 on the outside of our absolute value. So the first thing we have to do is divide both sides by negative 9. So that goes away. So now we have the absolute value of m equals negative 63 divided by negative 9 is a positive 7. So now our absolute value is all by itself. It equals a positive number. We can split this. So we're going to have m equals positive 7 and m equals negative 7. There are two solutions because there's nothing else we can solve in there. All right, the last one of this section I'm going to do with you is number 11. Number 11. So we have negative 2 times the absolute value of 2p minus 3 minus 1 equals negative 11. There's a lot going on in there. So right off the bat, we should notice that it equals a negative number. But first, we need to get rid of everything else around the absolute value before we decide it's no solution. So we need to add this one over. So now we have negative 2 times the absolute value of 2p minus 3 equals negative 11 negative 11 plus 1 is going to give us a negative 10. Now we divide by negative 2 because we need to get rid of that. So now our absolute value is by itself of 2p minus 3 equals negative 10 divided by negative 2 is a positive 5. So it does give us a positive value here, so we can solve this. So we now is where we split it into the two equations. So we're going to have 2p minus 3 equals 5 and 2p minus 3 equals negative 5. So always changing the what it equals, both positive and negative. So now we solve these. So we're going to add 3 over. Add 3. So we have 2p equals 8. Divide by 2. So p equals 4. So there's one solution. P equals 4. Now we do the second one, still adding 3 over. But now we have negative 5 plus 3, which is going to give us 2p equals negative 2. Divide by 2. So p equals negative 1. 4 and negative 1. So for that one, p is both 4 and negative 1, since we have two solutions for these. Okay? All right. Okay, so for this next section, I should say, we want to state the domain and range of the piecewise functions in the graph. Use interval notation. So if we look at this first one here, domain, remember domain is your x values, range is your y values. So the furthest to the left this function ever goes is here at negative 2. So we have negative 2, 2. Now we go all the way to the right and see how far it goes. This is the furthest to the right point, which is at, so it's 5, 6, 7. So our domain is negative 2, 7. Now for our range, this is our y value. So it's the lowest this function ever goes. The bottommost point is right here, which is at negative 3. So our range is negative 3, 2. Now we look for the highest point, which would be up here at 6. So there is our range. So remember, domain is x values, range is y values. Okay? All right, so for each of the graphs below, write the interval that defines each piece of the graph, then write the domain of the entire piecewise function. So we have an example here. For this, it's giving the different intervals, so the different parts of the function to take and look at the intervals for those. So pay attention to inequality symbols, don't want pieces to overlap. So for 15, if we look at this, the first interval, what's the x value here? Negative 2. And it goes to 0. This is our x value, 0. Then we go from 0 for our second interval to 4. So we've got 0 to 4. And then the last one is from 4 to, what's this x value? 6. So 4 to 6. So now we look at the domain. We look at the very first value for interval 1, which was negative 2. We look at the very last value in interval 3, which was 6. So our domain is negative 2, 6. So we're just breaking it down into smaller parts to then find the overall domain. For 17, so far you've only seen continuous piecewise defined functions, but piecewise functions can also be non-continuous. In fact, you've had some real-life experience with one kind of non-continuous piecewise function. The graph below represents how some teachers calculate grades. Finish filling in the piecewise equation, then label the graph with the corresponding values. So we are looking primarily here at our values here. So for an A, so this is telling us for an A, what would the range be? Now, different places do different things. I'm going to do this by tens, so keeping it nice and even. So this is a little different from our own grading scale, but it'd be 90 is less than or equal to x is less than 100. For a B, 90 would be on the high end now, and we'd be at 80 for the low end of B. So then 80 goes here, and then 70 will go here. So now 70's here for D, and we have 60 for the low end of D. Then for the high end of F, it's 60. For the low end of F, it's 0. So this would be our F. This would be D, oops, C, B, and A. So those would be the parts of our grade. So you notice it jumps. It's not a continuous thing. We're at 0 to 60. We're at 60 to 70, 70 to 80, 80 to 90. We don't have that continual line connecting them. So this is also a step function. Okay. All right. The last thing we're looking at, we want to write the piecewise equations for the given graphs. So we're going to look at number 19 together. So if we look at this first part here, so we have two parts. So that means we're going to have two equations and we have to do the intervals for them. So we'll have f of x equals. Now for this first equation, if we start from this point here, we go up 1, 2, 3, 4 over 1. That gets us to an exact next point. So that means our slope is 4x. Now to find the y-intercept, well, we're down here at -1. If we go down 4 more as part of our slope, we'd be at -5. And then we go over 1, we'll be on the y-axis. So that means our y-intercept is -5. Now, for our next equation, we look at this. Neither one of these points is at an exact location. So what we need to do is calculate the slope. So remember, slope formula is y2 minus y1 over x2 minus x1. So we have this point here is at 3.5. So that's our x value. It's our first x value, and a y value of 1. So they're going to be the second part of each of these. Our next one is at, 5, 6, 7 for an x value. And our y value is at 1/2, so 0.5. So if we take 0.5 minus 1, we get a -0.5. And if we take 7 minus 3.5, we get 3.5. So if we take a -0.5 divided by 3.5, we get -1/7. So that means our slope is a -1/7 x. Now to find the intercept then, we need to take, and we can use these points to help us. So one way to take and write this equation then is using point slope form. So we have two different ways we can do this. The way we're going to look at today is having it all on one side, since obviously with our piecewise function notation, we can't have it on both sides. So remember, point slope, or one version of it, is y equals m times x minus x1 plus y1. So put a parenthesis here. Use our x value of 7, so -1/7 x minus 7 plus 0.5. Now, we still need the intervals for these. So for the first equation, we went from 1 is less than or equal to x is less than or equal to, we went over to 2 and 3. So it's over at 3. I know this is kind of hard to read. Now, the second one, we were at 3.5, so 3.5 is less than or equal to x is less than or equal to 7, because that was as far as this went. So you have to have the intervals. You need both the equations and the intervals for which the functions exist for these, okay? All right, the last part, transformations on quadratic equations. Beginning with the parent function, f of x equals x squared, write the equation of the new function g of x that is a transformation of f of x as described, then graph it. So the one we are looking at today